Okay, good morning, everyone. I hope you can hear me clear, right? So this session will be recorded, and after the sessions, I will try to upload to the YouTube again, lah, so that you can refer to it. And for those who can't attend these sessions, you can also refer to it later on, right? So if you have any questions, feel free to stop me through the chat or maybe through the call, the voice, right? Okay. So today we will go into the chapter number 6, okay, which is related to the isoparametric formulations, right? So I guess we are quite how should I say ahead of schedules, okay? So we have some rooms to schedule our lecture later on, right? So you may have some more time to do your assignment and other things, right? Okay, so for this chapter, again, it will be related to the CO1 and CO5 actually, all right? So basically this isometric formulations is just an exposures to you, okay, on what actually happens, okay, more on the mathematical part, okay, on the usage of the knowledge of maths and engineering to solve the finite element problem, right? And at the same time, at the second stage or second part of this lecture, we will also discuss about some of the things related to the finite element software, okay, on how they actually do the calculations, okay, or how they can optimize their calculations, right, in terms of the storage, right? So in this recording, I will not put the video on, okay, to save the bandwidth going out, right? So I'm not sure whether it is because of UMS blocking the software sending out, okay, that I cannot stream, or I'm not sure, okay. But yeah, we will continue with the Google Meet for these sessions, right? Okay, just a recap on what you have seen previously. Okay, so this slide is actually on the lecture 1B, okay, when we mentioning about the FEA software. Okay, so in the FEA software, okay, where we talk about using a Lisa FEA software, okay, so we have discussed about some of the characteristics of the final element software, okay, and one of it is I have mentioned earlier, okay, we say that all the elements in the Lisa elements library are isoparametric, right? So this is where the terms comes in, right? So I have highlighted this briefly in that sessions, okay, what you will being exposed with this isoparametric formulations later on, okay? So today we will talk about this isoparametric formulations, okay? So most of the finite element software, indeed, they are using this isoparametric formulation instead of what we have used previously, okay, what we have derived previously, okay? Don't get me wrong that what you have learned previously is not useful, okay? It's served as the foundations, okay? And from there onwards, this is how we can relocate or remap our formulations into a new type of coordinate system, okay? We call it as a natural coordinate system, right? So these chapters will introduce you with the isoparametric formulations of the elements stiffness matrix, okay? So previously, again, you are exposed with the direct stiffness matrix formulations, okay, where you can easily grab, okay, after you understand how you can formulate it, right? You are taught about how to start from displacement functions. Then from the displacement functions, you learn about how to derive or to obtain the shape functions later on, right? So from there onwards, you develop the relationships between those stress, strain, and so on, okay? So here you can see that in this isoparametric formulations, it's basically the steps taken to formulate is the same. Okay, you still go through the 7 steps. Okay, the only difference is that instead of using a global coordinate system, which you have used previously, like the x, y, and z coordinate, or maybe some cases you may want to use Cartesians, those common or coordinate system that you are familiar with, right? But then for the computer itself, okay, for human, okay, we can easily understand those x, y, and z coordinate system, okay. But then in terms of computer, right? So computer, they don't have the real brain, all right? So what they did is they only recognize numbers, okay? Or maybe, yeah, most of them is numbers. So what happened is that we may want to develop this isoparametric formulation such that it is easier for the computer to program, okay, for it to be programmed, right? So that's why this isoparametric formulation has been widely used in most of the finite element software, right? The idea itself may seem tedious and also confusing, right? But then in general, it is much easier to program, okay, in terms of reflecting the nodes positions to this so-called natural coordinate system instead of the global coordinate system. Okay, so you may have a draw it in a model which you think is in the XYZ coordinate system, but in the program itself, they will translate all this into a simpler form of a natural coordinate system, okay, in order for them to solve it using the so-called isoparametric methods, okay. So now we will look into this, okay. So this isoparametric formulations will allow the elements to be created in a non-rectangular way, okay, just as any maybe trapezium shapes or whatever it is, and it can also have a curve shape, curve side as well, okay. So that's why it is very useful for the computer to actually model and calculate later on, right? So here is the isoparametric formulations for, I would say, a Q4, right? Quadrilateral elements, okay, at the beginning, right? So the terms isoparametric is actually derived from the use of the same, okay, iso, right? Parametric, this is referring to the parameter, and in this form, we are referring to the shape functions or the interpolation functions, okay? So that's why from the earlier part of the chapters, I have specifically mentions about the importance of the shape functions, okay? And we also know that the summations of the shape functions for all the nodes should be equals to 1, okay, for the same elements and so on, right? So this is why the shape functions is important, okay? It's actually form the fundamentals of this so-called isoparametric, okay? So this same shape functions will later on define the element shapes, okay, as they may be having the same displacement functions, right? So as you can see here, right? So the shape functions here is, this is the general shape functions, okay, which is related to the normal coordinate system that we used to know, all right, the x and y, okay, in terms of planar coordinate system, right? Maybe a plane, right? So two-dimensional coordinate system, x, y, right? So you have seen this shape function, so-called displacement functions previously, okay, in the previous chapters, right? The planar chapters, and the shape functions, one of it would be in this form, okay? B minus x, h minus y, divided by 4bh, right? One of these, right? So in terms of the isoparametric formulations, you can see that the relationships actually are similar. We still use the same displacement functions, okay, or I would say similar type of displacement functions, such that now instead of using S, okay, we use a natural coordinate S and T, right? So this would be our new coordinate system, okay, S and T, right? So parameters still the same, okay? The constant A1, A2, A3, A4, okay? X now replaced with S, okay? Y replaced with T, and so on. So from the same shape functions, okay, similar shape functions, only parameter change. So what you would expect, you would expect actually the exact same shape functions, okay? That is the idea behind this so-called isoparametric formulations, right? So this ST, okay, ST coordinate, we would call this as a natural or maybe intrinsic type of coordinate system, which defined according to the element geometry, okay, and not according to the coordinate system, okay. So you will later see how we would attach it to this coordinate system to our elements, right? But when we start with a two-dimensional or the bar elements, you may not see the huge difference, because for a bar elements, right? For a bar elements, we still attach previously this is X, okay? So naturally, if we attach a natural coordinate system, the natural coordinate system still along the X directions, okay? So in the bar type of axial coordinates, you may not see the real benefits, okay? It's still same, okay? As it's only depends on the S, okay, now being converted to S already, okay, X to S, right? So you would see the benefits later on, okay, when we move into a higher order type, or maybe a Q4 type of elements, right, which we'll discuss later on as well, okay. So in terms of the S and the X now, okay, so in order for us to make some useful relationship between them, okay, we need to build a relations, okay, we call it as a transformations mapping, okay, to define what is the relationship between this natural coordinate system as well as the global coordinate system for every single element, right? So this is what we need to do additionally when we use the isoparametric formulations, right? So the rest would be very similar, right? So now we will start with the bar element, okay, derivation for a bar elements, okay. So as I mentioned, the derivations would be similar, okay. You should expect the similar type of shape functions, okay. Only the difference is the formulations or the formulations of the coordinate system, okay. Previously we would attach as X, okay. Now we would define it as S, right? And also this S axis, we would say that it may not necessarily parallel to the x-axis. They may not necessarily parallel, okay? But in these bar elements, the best coordinate is parallel, okay? The best or the most convenient one would be parallel, okay? So that's why you may not see the huge difference for this bar element for now, okay? But later on, you may understand, okay, when we go into the Q4 elements, okay. But just take this, they are now using two different coordinate system, okay. This is the previous one, how we derive using X, okay, and this is the new one, okay. We are using the S coordinate system, okay, S coordinate system, okay. So in this S coordinate system, we will start to define it. Usually we will put at the middle, okay, the center of it, and we will locate it as 0, okay. So whatever to the left and to the right of this centroid or the s equals to 0 positions, we will have 1 and minus 1. Okay, so this is how we form our coordinate system. Okay, instead of getting this, maybe x1 is equals to 0.215 millimeter. Okay, and then this x2 is 0.3718. Okay, so you can see that computationally, okay, they do the same thing. Okay, they do the same calculation, but then for the computer to get all these exact coordinate systems from every single elements would be not, I would say, not efficient or not optimized. Okay, so therefore this isoparametric or natural coordinate systems comes in to define a simpler form of coordinate. Okay, just define it as 0, then whatever to the left is -1, to the right is 1. Okay, it's very straightforward. Okay, so that's why it would be more efficient, okay, in terms of them. Okay, what we need to add in, or the computer need to add in, is just to map this so-called s equals to 0, map it to where is the actual locations in the global coordinate system. Okay, that is the idea behind this. Okay, so what we need is a transformations mapping, okay, to map the x with the s. Okay, so that is the difference, right? So as you can see previously, okay, we would say this is -1, this is 1 in terms of s, right? And the middle one, the s would be equals to 0. Okay, so in terms of x, okay, so this x we would say as a central xc. Okay, xc, all right? And now we would define this as a length, right? Length itself, length of the element. So it would be easier now for us to actually form these transformations by referring to where is the coordinate, okay, of this centroid, or this s equals to 0, and what is the length. Okay, then from there we would able to define what is the positions of, or what is the coordinate for this node, and what is the coordinate for this node. Okay, that would be the computational part, right? But when you do the solutions, okay, you just multiply by 1 or other things, so it would be much easier, okay, for the computer to compute. Okay, the computer only need this one. Okay, this is -1 positions, and they will able to calculate, right? So the x positions now has been properly mapped, right? Because we know the length and the centroid is always at the middle. Okay, so L divided by 2, okay, plus, okay, you get the 1, right? The -1, okay, you get the minus the 1/2, so you get the exact coordinate of it, right? So based on that idea, right, also we can actually get the centroid, okay, by taking the average of the two nodes. Okay, yeah, the average of these two nodes, right? So the computer only have to get one time, okay, then they can get the average, okay, to form the transformation matrix, right? Then from this also we actually can know the length. Okay, so the length of the elements basically is x2 minus x1, right? Okay, assuming x2 is x2 is over here, okay, x1 is over here. Okay, so these positions minus these positions, you get the length, right? So rearrange or put these two inside, right? So eventually rearrange, you will get this natural coordinate relationship. Okay, s equals to x minus so on and so forth, right? So for us as human, this looks complicated and unnecessary. Why we need to transform all these things, okay? But for the computer, it is much easier, okay? Because they only have to know this position is s equals to 1, this position is s equals to -1. They don't need to know what is the actual coordinate, right, for their computations, right? So that's why in terms of isoparametric formulations, for computer, it's much easier for the programmer or for the program to actually compute. Okay, they just put s equals 1, s equals to -1. They don't have to keep looking, okay, where is the location, what is the coordinate, okay, to do the computations. Okay, they only need to do it once, okay, to compute the matrix, okay, the transformation rate, the transformation mapping relationship or the matrix. Okay, once we get that, okay, the computer get that, then the rest is just normal formulations, right? So once we relate this, basically, once we get this, okay, so eventually it is the very similar to the global coordinate as well. Okay, you still have the A1 plus A2S, right? The same form of the displacement functions, okay, that we use to derive for a bar element, right? Now what we need is we from this so-called X, okay, we just use the same concept, okay, put it in, okay, resubstitute, okay, we can form the matrix, okay, in terms of the shape functions, okay, our displacement functions, okay, can be rearranged in the form of the shape functions, where the shape functions for n1, okay, not 1, and the not 2 is given by this, okay. So these two shape functions, basically, if you derive it, okay, using the bar element, you would see the exact same or similar form, okay, of shape functions. Okay, that's why we would call this as a the same parametric or the isoparametric formulations. All right, so the idea remain the same, okay. As we understand the shape function is actually represent what is the contributions of the displacement for every single node, right? So you may contribute for n1, okay, contribution at not number 1 or s minus 1 would be equals to 1, okay, whereas it's slowly the weightage of the contribution of the displacement due to the node number 1 slowly linearly decrease, okay, whereas on the other side linearly increase. Okay, so that's why when you total them, these two shape functions together, you would get the summation should be equals to 1. Okay, you always comply to this particular rules or completeness of the rules itself, okay, for the shape functions. Okay, so this is how you can visualize the importance of the shape functions, okay, to reflect whether it is correct or not. Okay, then once you have the shape functions, okay, means after you have select the displacement functions, okay, as such, okay, then we can move on as usual, right? So the displacement function is now defined as the same shape functions, okay, as the elements, okay, and now since the u and the x have the same shape functions at the same node, okay, same node, okay, therefore if we compare it accordingly, okay, according to these two equations, accordingly, we call this element as a isoparametric, right? So these equations, okay, in terms of x or in terms of u, basically it's the same. Okay, so this is for the isoparametric, and this is for the usual I would say bar element, right? So this is for a usual bar element. So exactly the same form of matrix. Okay, so therefore we call it as isoparametric formulations. Okay, so once we move on, okay, this part on the stress strain and the stress or the strain displacement relationship, it is similar. Okay, the only difference is that because we have a ditch from the X or the global coordinate systems and introduce the natural coordinate systems. Therefore, we need to differentiate it with respect to this natural coordinate system. Okay, so what we need to implement, because we have a relationship between the S and the x, right? So therefore, what we need, we just have to add a chain rule, okay, of differentiations, okay, such that we can relate them with the x and s as well, right? So just add an additional chain rule to this, right? So once we add that one, okay, we differentiate and so on, okay. So we get what we would intend to get, right? So eventually the differentiations of the du over dx is given as such, okay. And we also know that the du over dx is actually the strain of the elements in terms of x directions, okay. So put them in, okay, accordingly. So we have formulate in this form, okay. Is the form that are very similar to what you have derived for the bar element, okay, very similar form. All right, then also you can see that the b is now equals to minus 1 over l and 1 over l, okay, because of the usage of the isoparametric, okay, or the shape functions, okay, derived as such, okay, derived as such. So once we have the b, okay, we have the strain, okay, we can also obtain the stress matrix, okay, by using the Hooke's law, assuming it is still under the u part, okay, this particular before the u limit, all right, before it start to curve and fracture, right? So along this particular sections, okay, this Hooke's law still applies, right? Therefore, in most of the finite element software as well, when we do our simulation, we should understand that it's actually based on the Hooke's law, okay? And our calculations or our validity of our analysis mainly focus on this particular part, okay? After that, it refer to the nonlinear type of displacement, all right? It become uncertain, okay? And if you put in all those consideration of the nonlinear displacement, then yes, okay, you may also consider this particular part, okay? But that would be not, how would I say, being covered by this course, all right? So our main focus now only on this particular part, right? Only on the linear part of the displacement, okay? So once we base on the Hooke's law, okay, you will see that the Hooke's law is actually stress equals to the Young modulus multiplied by the strain, right? And we know that the strain is equals to BD, right? So you just have to put in all the metrics that you have formulated earlier, and yeah, you should able to calculate or to obtain or to estimate the stress, okay? So you can see that for the simple bar element itself, you don't see the real advantage, okay? Because you still get the same formulations, okay? But you have to add, how I say, additional work to differentiate respect to the natural frequency and so on, okay? The benefit is not clear for a bar element, right? Because we still use the same, how should I say, the same directions of the natural axis, okay, which is parallel to the x-axis, okay? So you don't see the much benefit of it, right? But that is the concept behind it, right? Then for the stiffness matrix, once we get that one, okay, as usual, we have to combine all the matrices, okay? Combine all the matrix, okay, across all the dimensions, okay. You may have more than one elements, okay, one directions and so on. So combine them together by taking the integral, right, of the elements, okay, along the whole length of the whole your problem, all right. Then from there also we need to transform the coordinate of x to s, okay, x to s, okay. So this is in terms of x, okay, okay, x equals to L, right? So we need to transform it equals to s equals to 1, okay, s equals to -1, right? So this is how we have relate it, okay? And internally, you can see that there is a modulus, okay, or the determinants of the Jacobian matrix, right? So coincidentally, because of this is a one-dimensional cases, the determinants of the Jacobian matrix would be equals to the Jacobian as well, right? So the Jacobian matrix is given as such, right? This is how we define or call this as a Jacobian matrix, okay? So for a simple bar element, once we put it in, okay, the determinant of our Jacobian matrix would be equals to the dx over ds, which is equals to the L over 2, right? So this is what we put into our formulations, okay? Then from there onwards, okay, we would plug in the B matrix, okay? B matrix, inverse transform, okay? So this is what you would you can derive, okay, or expand onwards, okay? So this L over 2, right? Put all this in, okay? Rearrange. Eventually, you will see that there is LAE, right? Okay, K equals to LAE and this matrix, right? So if we further factorize this L over 2 out, okay, eventually we get the K equals to AE over L, 1 minus 1, 1 minus 1. And this is the exact same stiffness matrix that you have obtained for a bar element previously, right? So again, as I've highlighted before, okay, so for the bar elements, you would need the AE to be defined, where the L itself, the software can obtain it, okay, from your model, from the coordinate, but the A and the E, you have to tell the software, okay, what is the Young modulus and what is the area, right? So you can see that in the Lisa FEA software, okay, you may define this over here, right? So there is the cross-sectional area, okay, for the material property, okay? When you define the material property for your bar element, okay, or yeah, for the line element itself, okay, they may provide this blank empty space for you, okay? So you may want, or you may need to define what is the cross-sectional area, okay, in order for the analysis result to be meaningful, to be meaningful, okay? Otherwise, if you don't provide A and E, the software will still carry on run for the, how would I say, the solutions, okay? But then you may get a strange results, maybe, okay? Because by default, okay, if you don't put, the software may put either 0 or 1, okay? If they put 0, then 0, 0, so the stiffness is 0, okay? So this is how they would do, right? So that's why understanding of what are the parameter or the formulations of the elements itself is important, okay? So that you know what is the important material property or parameter that you may need to define, okay, in order for that particular analysis to be meaningful, right? Otherwise, what you analyze may not be meaningful, because you may analyze, you get the stress is maybe 10 megapascal, but you put the wrong Young modulus, or maybe you put the wrong or you didn't define the area, okay? That's why you give you different kind of answer, right? So the computer will only give you whatever they can compute in numbers, okay? But then you, as the user or the knowledgeable user, you should able to define, okay, or to supply what kind of information they need, okay, and to interpret later on whether it is correct or not, okay? So that's why eventually the basic calculations, like what you are asked to do in your assignments, okay, you need to compare it with different elements, and then also the classical beam theory, okay, in order for you to actually see whether the result is close enough or not. If it is not close enough, then maybe something is wrong. Either the selection of the element is not proper, or maybe you miss out putting some of this parameter, right? Okay, so this is exactly the same with what you have learned previously, right? Okay, so next would be on the boundary conditions. Okay, so for the boundary conditions, basically the idea is still the same. Okay, what is important is that you should able to to know. Okay, just to know. Okay, ideally, because nowadays most of the software you just have to click. You have the GUI, you just click and so on, right? But internally, what they actually did is that if we, let's say, we use a three-dimensional object here, okay, to visualize, okay, for a body force, right? So this is a three-dimensional object, okay, outside this one, right? So this one is your three-dimensional object, okay? So internally, you can actually break this one small cube, okay, out, right? So you may break this into a cube, right? And that we call this as an element, right? So in this element now, okay, it has a body force, okay? This body force may be in the form of mass, okay? There is a mass, okay, which create the force, okay, in the gravitational directions, okay? So therefore, in this way, okay, when we transform into the formulations of FEA, we have to transform this particular force into the so-called nodes, okay, that form the element itself, right? So this is the idea for a three-dimensional body force, right? But then for sure, now we will start again with the two-dimensional, okay, just two bar, right, and so on, okay? So in this particular body force, again, it has a mass, okay? So anything will have a mass, right? So this mass can be defined by maybe density, right? Because you may define the volume, okay? You may define already the volume, okay? Then you have a density, right? So this density will actually interpret as the body force per volume, okay? Because density is M over V, right? Okay, the mass over volume, right? So this is where the body force will comes into play, right? Again, now you can see an additional parameter that you may want to tell the software, okay, the mass itself, okay, when you would want to consider the body force, the weight of the object that you are going to analyze. All right, so in terms of formulations, okay, this is just an exposure for you. All right, the body force matrix is defined as such. Okay, you have to integral along the three particular axes, okay, over the whole volume of the elements. All right, yeah, for the elements itself. Okay, then once we take into parts, okay, we discretize them into parts, okay, according to our elements. Okay, this is only a two-dimensional elements which only involve N1 and N2. Therefore, you will see that there is a L, right, the beam element, the bar elements, okay, and now they come this as XP. Okay, what is this XP? This XP is referring to the body force per unit volume. Okay, or in other words, body force per unit volume, which is referring to the density, right? So in order for you to take into the consideration of the body force, okay, you have to define an additional density, okay, for the software to take into account, right? So the body force will be equally distributed to the two nodes, okay, since this is a bar elements, okay, whatever acting, then we have to divide them, okay, distribute them equally to these two particular nodes, okay, because as we say, no forces would be applied, okay, no forces will be applied at the middle, okay, all the forces will be applied at the node, right? Therefore we have to equally distribute them according to the nodes, right? So this is for a two-dimensional cases, okay. Later on you will see that the three-dimensional cases will have the same ideas, okay. You just have to, instead of two nodes, now it will become 1 2 3 4 3 5 6 7 8 nodes, okay, equally divided by the 8 nodes itself. Okay, next would be the surface force. Okay, surface force, as we can visualize it, okay, surface force only acting on the surface, okay, therefore whatever elements inside the body uh, may not be subjected to this force, okay. This force only subjected to those elements which is connected to the surface, right? So again, if we take these elements out, okay, it would be similar to this. And if we further from the elements convert it to the force acting on the nodes, it should be acting on the nodes, okay, of that particular subjected surface itself, right? So the surface type, okay, is very straightforward, okay, only integrate it with respect to the surface, okay, surface in the x and y directions, okay, probably, and the forces acting on the surface would be in the form of Tx, okay, in the form of unit of force per unit length, okay, how much force they actually act, okay, along one unit length, okay, so that would be the Tx, okay. So when we multiply this Tx by L, it represents the total force, okay, the Fs, okay, total force actually acting across the whole surface, right? So that's why the Tx is just the unit force per unit length, okay. The uniform surface tractions or the forces itself again will be distributed into the nodes, okay, corresponding to that particular surface, okay. And these examples, what we are discussing is again referring to the two nodes, therefore it will be distributed to the two node itself, right? Then the amount of forces allocated to each node would depends on the Tx, okay, where is the locations, and it would be found by the integrations, right? So that would be the first part of the derivations for the bar element using the isoparametric formulation. So if you have questions, feel free to ask. If no, we will proceed, right? Any questions so far? Okay, I guess no. So I will continue with the second part, all right? So the second part would be very similar, okay? Once you understand the idea behind it, now you can see we will use a Q4 element, okay? The same ideas, okay? And apply it for a Q4. And because of the Q4 now, okay, instead of taking how should I say, a rectangular orthogonal type of elements, those elements, when you mesh it, okay, it can be taken in any shapes, okay, sorry, okay, it can be in this particular form of shapes, right? Therefore, if we use a natural axis, okay, S and T, now we can define it, okay, attaching it to the S, okay, and as well as T, right? So here when we define the coordinates according to the S and T, okay, or to this natural coordinates, it doesn't need to be orthogonal, right? Or and parallel to the X and Y axis, okay? What you need is that you know that at this particular point, okay, this particular node, it must be 1, okay? In terms of, how should I say? Okay, let's draw longer, right? So you would see that this point is -1, okay? This point is 1, right? And this point is -1, and this point as well is 1, right? So in terms of coordinate, okay, you just have to map it, all right? This knot, let's say this knot, right? So this knot basically will take as the S, which is -1, and the T is 1, right? In the natural coordinate, very straightforward, okay? Very easy to get, okay? For this knot number 3, this would be 1 and 1, right? So you don't have to take the parallel side and also the orthogonal. So it will just reflect directly like this, okay? That's why in the computational way, it's very easy to formulate, right? So you will get this ST coordinate, right? ST coordinate. But remember, you don't need to be orthogonal like this, right? So that is the main benefit, okay? When you relate this natural coordinate with the global coordinate, the actual coordinate, which is the x4, y4, and so on, then that would be the mapping of the transformation mapping between the ST coordinate and the global coordinate system, right? That would be handled by the particular matrix, okay? Therefore, in the program itself, okay, when you do the programming of this Q4, it will be now much more easier, okay? You don't need to exactly get the value of the x and y coordinate, okay? You just use the -1, 1, 1, 1, 1, -1, and so on, okay? To calculate what is the stress by that particular element, I would say explicitly, right? So for the global coordinate systems, again, you can always relate them, okay? This is the relations, okay, between the S and X, okay? And then for the Y coordinate system, the Y and the T, okay? The idea is still the same like the previous bar element, right? Only add the T coordinate or the T coordinate, right? So as you would expect, the shape functions now would be exactly the same, okay? Instead of X and Y, it would now become S and T, S and T, S and T, okay? Very straightforward. And then the displacement function can be expressed, okay, in this form, okay? Exactly the same, just take it and just change the S and T, right? So if you still recap, okay, you can recall back, okay, this is the slide that you have seen in the previous lecture on the Q4 formulations, okay, where you can have the shape functions of it, okay, you will take on the knot one and you can check it, all right, such that the N1 is at the half, all right, the B1 over here is full, right? So when the X position is over here, you just substitute minus B over here, right? Okay, then you will get the full value at this particular point would be equals to this, right? So that is the idea, okay? So this is how it would looks like, okay, if it is formulated for the Q4, right? In terms of the global coordinate system, is exactly the same with the isoparametric formulations. Only the difference is the S and T, right? So next would be similar, okay, for the strain displacement and the stress displacement relationship. The ideas remain the same, okay? You just have to take care of the chain rules differentiations. Again, then you form the relationship, okay, between the displacement and the strain, and then between the strain, okay, this represent the strain, right, and the stress itself, right? So for the body forces as well, it would be similar. You have to integrate for the whole volume, okay, in terms of S and T, right? Okay, and you will notice that the force would be in terms of 8 by 1 matrix, okay, because you have 8 knot, right? 1, 2, 3, 4, 5, 6, 7, 8. All right, so same thing, okay? You will get the body force, okay, and this body force, what is required, the same formulation as previous. you would need the density, right? If we are talking about the mass, okay, the mass of the object itself. Okay, then for the surface forces, same thing. All right, because the surface only involve 4 nodes, okay, on the particular selected surface, so therefore it's 4 by 1. Okay, and you just plug in all those relevant matrices, you should get the force acting on those 4 nodes itself, right? So that is the ideas of the isoparametric formulations. Okay, so if you have questions, feel free to ask. Okay, and while we'll discuss about these two questions. Okay, the first questions would be, what are the material properties required for a 3-dimensional structural analysis? Okay, so if you look at your understandings on the previous 2-dimensional analysis, okay, what you need is the AE over L, right? You need the area, you need the length itself, okay? Hey, sorry, the E, the Young modulus itself, okay? To obtain the stress and the displacement, okay? But then how about a 3-dimensional analysis, okay? Once you understand the idea behind those formulations, what you would need to check is the relationship between the strain and the stress. Okay, so this is the relationship for a 3-dimensional structural analysis, okay, which involve this particular terms. Okay, so these particular terms would have the B matrix, again the same, okay, but then you have the E matrix, okay, and also the V. Okay, therefore for a 3-dimensional structural analysis, what you need is the addition. Beside the Young modulus, you also need the Poisson ratio. Okay, so this is the analysis obtained from one of the paper, okay, related to a corrugated core sandwich panel, okay, which is modeled in a 3-dimensional form, okay, undergoing a 3-point bending test, okay, in a simulated way, right? So this analysis itself in this paper, they reveals that the material is ABS, okay. Then in order for this particular analysis to be completed, it's also require the Young modulus, okay, to be defined as such, okay. Then the Poisson ratio, because it depends on these formulations, right? Besides that, also we include the density, right? Because there is a body weight or the body force, okay, applied to this, okay, for sure, because you can see another material property or parameter that have been inserted to the analysis is the coefficient of friction, because we are modeling the contact, okay, between this loading nodes as well as on the specimen itself, okay, during the simulations, right? So this is the idea, okay. Once you understand the formulations that you have start to derive from the early days, okay, the chapter 2 until today, okay, you will see that the important things that you need to take care is you need to know what are the material property or parameter that you as a user should supply it correctly to the software. Okay, that is your own assumption. You assume that is correct, okay, and you supply it to the software. Okay, so how you obtain all these Young modulus and Poisson ratios? Again, we assume the material is homogeneous or maybe perfect. Okay, no notch, no defect, right? So therefore, we may take the Young modulus from maybe the appendix of your material design textbook, okay, for the particular material and so on, okay. That is where it comes into play, right? To estimate, remember, to estimate, okay. So whatever you learn, is to estimate. Remember, final element is to estimate, okay, or to approximate what would happen, all right? But for sure, in real, there are a lot of other defects and other things comes in, okay? So if you can do some testing of the material that being used as well, okay, that would be greater, okay? Instead of taking it directly from the books or the appendix in the textbooks, okay? Because those appendix in the textbook, you may not know what are the conditions of the material, okay? It may be slightly different, okay, in terms of the process, okay, that give you the different characteristic of the Young modulus as well as the Poisson ratios, okay, right? So next would be the second questions, okay? How computer do integrations, okay? Because we have mentioned that you have to integrate respect to body, volume, or surface, right? So how computer actually do integrations, okay? So I believe you have learned this in numerical methods, okay? You can do integration using several numerical integrations methods such as Newton Cortes, okay? And the second one will be the Gaussian's quadrature, okay? Quadrature. So these two methods are quite famous, okay? Are widely used, right? To approximate the area under the curve, right? So you may either use a trapezoid rules, Simpson 1/3, Simpson 3/8, and so on, okay? So this is how you can relate it with what you have learned in the numerical methods, all right? Then next would be on where you can see all these methods actually being applied is that you can see this some software, okay, especially those commercially widely used software, okay, for example, is Abacus, okay, Abacus or ANSYS, they are widely recognized, okay, widely used commercial software, okay, and all this software, okay, they allows you to customize, okay, in terms of what type of methods, what type of formula to be used in that particular system, okay, therefore, for example, in this Abacus, you can actually see or define what type of integration methods to be used, okay? So by default, okay, they use a Simpson rules, okay, to integrate for the shell sections, okay? But then you can also set it as equals to Gauss, which refer to the Gaussian's quadrature and so on, okay? So this is how you can change it according to the integration methods that suits to your needs in your final element applications, right? So this is the Gaussian quadrature methods, okay, where it's again widely used based on the optimized position of the sampling point, right? So this sampling point or the integration point itself, okay, is again a terms that you commonly heard, okay, in the final elements, okay. You have a Gauss point, okay. So this Gauss point actually refer to the location of the Gauss positions, okay, your sampling positions, or the integration point, okay, which referring to the point, okay, where you would integrate, okay, your particular point to reflect or to represent that particular area, right? So those point is where when you do the stress analysis, okay, the software will calculate and they will calculate, integrate, and do summations, multiplications at the particular point, okay, or we call it integration point, Gauss point, okay. Therefore, in some software, when you play around, then you say sometimes you will see the terms called integration point or Gauss point appear in your software, okay. This is where it refer to, okay, the locations of the integration point of that particular element, right? So for Q4 element, all right, for a Q4 element, there is 4 Gauss point, okay. You have 1, 2, 3, and 4 Gauss point, okay, to represent this particular Q4 itself, and those stresses actually being computed or total R multiplied at this Gauss point, right? So that is the idea, okay? So overall, for evaluations of your metrics, we still follow this particular flow, right? You may have the algorithm. Yeah, the algorithms first to read the 4 Gauss point for Q4, then what is the weight functions, okay, which referring to this, okay, the weight functions, okay, the weight functions of it, okay. Then from there, you assign, make sure the stiffness matrix is zero at the beginning. Then we do a looping, okay, for every single node itself, every single Gauss point itself, okay. Then what we do in the looping is we will let S equals to so on, okay, compute the matrices, okay, compute the stiffness matrix, assign it back, right, until all the Gauss point have the relevance information of stress matrix, and then you would start to do all the stress analysis and the displacement analysis, right? So that's would be the part related to the isoparametric formulations. Okay, so any questions again? If we don't have more questions, then maybe we will stop for these sessions. Okay, I don't want to have very long sessions. Okay, so we will stop and we will continue on the storage of the stiffness matrix in the next lessons, okay, on this Thursday, right? So see you again.
One more question before we end the class. Sir, can I ask a question?
Yeah, sure.
Regarding the assignment goal, uh, when we do the sim like we do the simulation, do we
Yes.
also need to do theoretical calculation?
No need. You just have to do the simulations and then you compare it with the classical beam theory. That's all.
Or
Ah.
you mean like there's four type of, for part one there's like four type of meshing
Yes.
we have to do, so we compare among them
Yeah.
lah.
Yeah. You just use the software to compare.
Oh, okay.
No need to do the handwriting calculation because I know the meshing will be more than that. Okay, it will take you a lot of time.
All right.
Okay, just use the software.
Same for part two, only just use the simulation to do our
Yes.
analysis.
Yes. The most important part that I would look into would be your discussion, how you would model it, compare it. All right.
All right.
Okay.
Thank you, sir.
Welcome. Okay, so if no questions, then that's all for today. Okay. Thank you, everyone. Bye-bye.
Thank you, sir.
Thank you,
Thank
sir.
you, doctor.
Thank you, brother. Bye.
Thank you, sir.